This time around, we're going to see if we can run our performance tests inside of our own compute instance on the Amazon account. This is going to give us some benefits over the previous test that we ran last time around in Grafana Cloud. Given that I don't actually have a paid license, we're quite limited to 100 virtual users. Although it's quite a generous amount of users, we want to actually put Lambda effectively under stress and see how far we can push that to work out how viable it will be as a solution, and also then get a comparison between it and ECS. So in doing that, we want to be able to go way above 100 virtual users. So in doing so, what I've got here, I've actually put together a similar test suite to what we had before. So if you remember from the previous video, we have this HTTP test which we're running with a set of users. So we've got our 100 virtual users, and it's effectively just requesting our static React app and its various components. So it emulates what a browser would do per request. This time round, I've got the same set of requests that we're doing. So the test is effectively the same, including the same half-second sleep. And what I've done is I've defined a different set of profiles. So these profiles range from light to excessive. I was kind of stepping it up and working through different levels of testing that we would want, to work out whatever our maximum utilization is going to be, our desired utilization. So in here, you could define any number of different profiles. I've started with a light one that's 50 users. It's actually less than what we were running in the cloud on the last test. Moderate, 250 users, and then we start going up into heavy, very heavy, ultra heavy, and excessive. You could call these profiles anything you like. They just happen to be the levels that I was working on, and from what I've roughly figured out by putting this together, I think where we're going to sit today is probably this ultra heavy range, which is around about that 3,000 virtual user mark. The Amazon account that I've got at the moment has the default execution concurrency of about 1,000 lambdas, but even so, based on the way it was scaling and everything else that was going on, including the test host that we will be using today, 3,000 users was about optimal to make sure that we didn't saturate that test host or what the account was capable of doing. We want to make sure that the performance that we get is equivalent. We don't want to see any bottlenecks due to hitting certain quotas or limitations. So that's going to be our target for this particular video. So I'll take you through it. So obviously we've got the profiles here, just as I've mentioned. I will draw your attention to the lower settings are only doing like a 1 minute test, and then within each of the larger ones here, we're doing a 2 minute duration. Ramp ups and cooldowns being a fraction of those. This kind of test, we're just trying to hit it as hard as we can to kind of get feedback on the performance and or scale capacity that it's able to do with a sudden influx of load. If you want to do true saturation testing, you'll want to change these durations and times. You maybe even want to have it dip for a while and come back again. You're going to run it for a long period of time and collect a lot of data. Obviously, that's going to cost you a lot more in Amazon cloud resources to do so, but that will give you a far better idea from a saturation perspective of how your end platform is going to perform. That's kind of out of scope for what we're doing today, so we're really just going to see what those kind of really peak heavy loads are like on a platform that may be a little bit dormant as far as Lambda goes, and then we're working out on the ECS side how much do we need to scale it up to be able to take the equivalent that Lambda just gives us out of the box. So that's kind of what our goal is going to be here. So this is all being Dockerized. We're going to run this in ECS. So in here you can see I've pretty much just taken Amazon's AWS CLI base image to put this on. I've installed Grafana's K6 tool into this particular instance. We've got an entry point, and obviously I'm copying in the test itself into a location. So this entry point, the reason this exists is we want to be able to get our test reports and keep them. So we're running this within a container inside ECS. Once the container finishes executing, it goes away. It's all ephemeral. So this entry point is what actually invokes the test run. So you can see here on line 5, we're going to run the test, we're going to output it to this file, and then that file itself is going to get uploaded to an S3 bucket, and that way we've persisted it and we can go back and retrieve it should we need it in future. So this is my basic attempt at setting up something that's kind of a bit of a general purpose test ground that we can repeatedly run things on. So it's its own little app that we'll deploy. It's also got a stack that we're deploying with as well. So I've put together just a very, very basic stack. It's actually kind of similar to our workload stack as well. And that's going to deploy our bucket, obviously, that we've got. There's a log group, CloudWatch log group for this particular process, so you can actually look at the test performance results as the thing runs. ECR repository, we need that to store our image. We've got our role to be able to actually execute the task within ECS, but then also for the actual task itself running to be able to do things like upload to S3, for example. So your S3 bucket put object permission is here. So there's 2 roles in there at the moment. We've got our security group. Don't really need to do anything with the security group. I've just put it there as a marker as this thing needs to be wrapped in something, and I may add ingress or egress rules for it at a later date, but at the moment things are just going out to the internet as far as this is concerned. Task definition, this is probably the most important thing. This is what we're actually going to run to execute our test suite. So this just has some base settings. All this can be overwritten at runtime. It points to the current artifact version that's going to be run, and we're invoking our entry point script that we just looked at before. We can provide our bucket as well. May as well point that out. The bucket name can actually be written, put in at runtime. So that's that. Our make file, it's been updated just to support all this as well. So we've got our build and our push of our image that we're building, same as with our workload. We had our build tasks and our pushing to ECR for those. So I've added this into the make file as well. It's becoming quite a large make file. It does lots of things, but at least it's captured as code. Our CloudFormation stack, so we've got obviously there's our validation of the templates been appended there. We've got our deployment of the load test stack itself here with our deployed load test task. And then the cleanup will obviously also clean up the load test stack along with our workload and everything else, given this is something that we're just spinning up to do tests work on. I've got a couple of tasks down the bottom, and these are the ones that we're going to use today for actually running this. And we've got our Docker one. This is designed for local Docker, so we would run our code that we've just built on our local Docker for testing. So in this case, we're using the light profile, and this will hit the current deployment that's out there, but it allows us to kind of test the code that we're using for what inside our Docker image that we're going to be running in ECS. So it's kind of the development environment, I guess you could look at it that way. And then we've got our ECS one, and this is what's actually going to go run our performance tests. We will just trigger this directly using the task definition I showed you in the CloudFormation template. There's a few overrides here. We increase our CPU, we increase the memory, and the container overrides, we can go and then configure the profile being used and all of that. So I'm going to go and run this now, and we'll deploy, we'll have a look at how the tests are running against Lambda. So the current workload deployed is our Lambda workload. So we'll go and run this, and then we'll be able to see how that's actually performing by default. So in looking at the results that we've got here, I'm estimating that we're probably going to need around 8 to 9 thereabouts containers to be able to get equivalent performance to what we've been getting with Lambda to date. So given that we're looking at our ultra heavy profile, which is 3,000 virtual users, being able to sustain that kind of load with these very small container instances that we're using inside of ECS, we're going to have to scale it out to quite a number. So there's a few options that you would normally have here with your workload. If you're persisting this kind of high load, I guess you could actually go and scale your instance up, and you can actually have more compute. So we've only got a quarter of a CPU here and half a gig of RAM. Now, if you're going to bump that up to half a CPU, just looking at Amazon's compute requirements alone for ECS, you're going to actually pay additional costs on memory as well. If we jump over here, we can actually have a look at their supported configuration. So if we're going to go from a quarter of CPU to half a CPU, we're going to need a minimum of a gig of RAM, which means we're now going to pay for an extra 500 meg of RAM as well to get that additional CPU capacity. So if you've got a really peaky, spiky load pattern going on your service, it's possibly not necessarily worth going and bringing your base instance size up to kind of meet what you're trying to achieve for your peak performance goals. You want to keep it as low as possible. What we're doing, because this is effectively just a load test scenario, we're comparing Lambda to ECS. I don't really need to go and test what exact instance size I need that's going to suffice for the peak load that I'm comparing to Lambda. I'm able to just scale multiple units of this out in 8 or 9 instances, especially in a production environment where you're going to want to have some form of high availability. That's pretty reasonable, and the cost is effectively the same. You just have more things of a smaller compute and memory footprint versus fewer with a higher capacity. So just something to keep in mind when you're doing your optimization for these kind of scenarios. Starting with our moderate profile, I've been slowly increasing the amount of virtual users that we're using in our tests here. So with our moderate one, you can see here we've had a user count of 250, which is still bumping up against maximum CPU usage on a single container instance. Our average is fairly low. I will caveat that the averages here aren't ideal, given that we're using Amazon's default metrics, and these are 5-minute averages. The test that we're running at the moment, running for about a minute and a half, so the averages aren't a true representation of exactly what's going on here. So to expect to see that this will be significantly higher as far as average consistent utilization of the host go. We could run longer tests and that will stretch this out a bit, but for the minute this is enough to kind of figure out what we need to do. So in running the tests, everything came back good for 250 virtual users, so we had no failures. I then moved on to running heavy, and we can see here that we've got a much higher average, and in doing so we also had a reasonable failure rate. So we can't do 1,000 virtual users against a single instance here, and that's not really surprising given the size of the instance. So over the last couple of hours, I've just been kind of running through and changing the amount of virtual users we've got to try and find a happy middle ground there and work out exactly how many users we're able to support on a single container instance. And I've worked that down to 370 virtual users seems to run without any errors at this stage. So I've kind of set that in as our baseline. We can still see that we're still spiking up and hitting the maximum there, but we're not sustaining that throughout everything. So you can see across here we've had, as I was doing various tests, anywhere between 500 and 1,000. I think I started around 750 here and was slowly dropping it down. We were keeping the utilization of the host still way too high, and the error rate was still present. It wasn't particularly high, it was only a small amount. Looking at our memory utilization, given that we're under 1%, we're effectively not using memory at all. This is likely to do with Nginx configuration as well as the load, so we could probably go and adjust some of the Nginx config there and actually get some better performance out of it. But given that we're just keeping everything really basic and standard at the moment, we're not going to go there. That could be something as a future improvement. But yeah, so in summary, after testing all this, worked out that the rough baseline for this particular setup is around about that 370 virtual users. Seems to be pretty reliable, which is good. Moving over to our load balancer here, we can see that most of the requests that we've got coming through are all successful, apart from the errors from the earlier tests that I've got. You can see ELB 500s there, spiking up particularly on the larger tests that I've run. As we've got closer and closer, refining it down, obviously we've got far less errors. I had a look at these 400s because these were quite perplexing. I wasn't seeing any particular failures that mattered. I have noticed that Grafana itself seems to look for a couple of files when it finishes tests. There's a .m file and some other file that it's looking for. Sorry, no, it's just a .m file. So yeah, it's requesting this .m. We currently don't have that as part of our setup, so it's not able to get that information. And I haven't actually configured Nginx to have a 404 file for it to be able to return. So these two requests here pop up after our tests are finished. So we don't actually see these in the failure results. This is something that occurs later, but obviously shows up on the load balancer dashboards there. I've also been seeing a few requests coming through from the internet, given that this is not actually running privately within the VPC. I'm actually using public facing infrastructure at the moment. These requests have come in randomly from the internet during the test, so that's what's causing these 400s against our target groups, and the 500s that we're seeing are pretty much just due to overloading the current connections against Nginx. So we can see we're getting 504s. So with that baseline, which is what I'm actually now going to call it. So I've actually added a baseline profile into our code here. So we know our container can support this in its current configuration. So any changes that we make from now on, we'll be able to rerun this baseline against a single container, and we can work out whether we've got an additional performance cost or some kind of trade-off coming in with those new changes. And ideally going forward, if we kept our container fairly much the way that it is and we just go and tune the Nginx configuration, we should be able to see that we can potentially shift that baseline and actually get improved numbers of virtual users on here, which would be an ideal goal to try and achieve as well. Let's take a look at the benchmark results now. In gathering these results, I've run the test through 3 times against each deployment style, and I've also performed a pre-warm-up run just to ensure that the load balancers themselves have been scaled up and don't interfere with the results. Something to take into account, I've realized over the time of developing this series that depending on the time of day and even month to month, that performance does seem to differ on the AWS platform, probably due to its utilization. So depending on whether you're going to run similar tests or even run the ones that I've got here, you may get differing results compared to what I've found here, but we should be roughly within the ballpark of what we're expecting. Here we have our baseline benchmark of our 370 virtual users. We've deployed our standard Lambda setup with 128 meg of memory and our single ECS Fargate task instance with a quarter CPU and half a gig of memory, this being the smallest possible unit that we can actually deploy. No tuning has been done on Nginx, and that's seen us hit the CPU limits as well on this Fargate task. So looking over at the results that we've got here, requests per second, we've seen Lambda itself get up to around about 4,000 requests a second, or just shy of, and this has been primarily due to it scaling the compute behind that particular function. ECS, limited to that single instance that's running at the moment, has seen just shy of 2,500, so quite respectable from both of them. On the below graphs, we're able to see waiting and duration time. Waiting's here to try and highlight any slowness in responsiveness from either Lambda firing up extra instances or ECS struggling with its CPU overhead in this particular case. We're able to see here that we've got pretty fast and snappy response times in the low end from ECS, and we kind of expect that a long-running compute instance there would be more responsive than a function like Lambda. But as we see with the test running through, Lambda's average performance, due to the scaling behind it, is far more responsive than the ECS task, with a 95th percentile of about 44 milliseconds for each response. We're kind of just using the 95th there to cut out the maximums. You can see there's been a few 10-second blowouts there with ECS due to the CPU contention. And we also had a couple of almost 1 second responses from Lambda as well. So if we take the 95th percentile of responses in, Lambda itself is performing exceptionally well on average here. And ECS, even at that load, is still quite respectable as well, around a quarter, just under a quarter of a second response times there for requests while under load. So in a non-prod environment, this is a really good setup for either use case. Obviously, we're looking for something that's a little bit better than what you get with a single instance. Taking a look at our high load test result, here you can see that I've limited our test to 900 virtual users, and this was just due to some instability that I was frequently seeing when I scaled the Lambda test past this. So just for repeatability, I've kept it here at 900. To match this, I've also scaled the ECS task count up to 3. And below you can see with these results, as we would expect using ECS, the connection setup times initially are quite punchy and far shorter than Lambda. And this climbs as we start to put more load on the individual services themselves. Overall, the average request duration from Lambda is quicker than ECS, and this is something that we'd expect as we start to see the function scale behind the scenes. ECS does scale fairly linearly, so increasing the task count will support greater volumes, and this is just something that we would expect to see in a standard operating mode. Both Lambda and ECS deployments could definitely see some improvements with some performance tuning. This is very vanilla and we've done nothing, as you can see in the code that I've attached in the description below. In future, increases to service quotas will allow us to go beyond the Lambda defaults, which is usually around about 1,000 requests per second for most accounts. In summarizing the performance test results, as mentioned, Lambda achieved an overall lower request duration, with ECS achieving the fastest initial response times. For our high load tests, we saw comparable performance from both deployment styles, and with some tuning, should be able to see stable Lambda performance beyond this level. A potential consideration would be to implement something like client-side retries, which could minimize the potential impact on users and still provide a great experience. Let's take a look at the costs of running these deployment styles. Here I've focused in on the cost of the compute only, with an estimate of 2,000 requests per day, and have excluded the expense of the load balancer and the data transfer. As a note, if you're not aware, AWS will charge you for data transferred between availability zones in your region, and this can be quite a significant cost as well and something to look out for, so a potential hidden cost there. The results here show that Lambda is coming in 99% cheaper when compared to ECS, with even the annual costs coming in at less than $1. It's quite impressive to see how much you could potentially save here with this approach. And on that note, it brings this short series to a conclusion. I trust you found this interesting and hope it provides you with some inspiration on different thoughts and approaches to running your cloud workloads. Is this something that would be useful in your organization, or maybe for a home project? Do you have other ideas on how we could save money while maintaining service levels? Please leave a comment and share your ideas below, and thank you for tuning in.